Alrighty, how are you all doing today?
Good, and yourself?
I'm doing fine.
Doing well. All right, let's go ahead and jump into this in-class assignment here. Shit, I went the wrong thing. Share screen. There we go. All righty. So this is a reasonably complicated total response problem. And I say reasonably complicated because we're looking for something maybe a little bit weird. We're looking for the voltage drop over a current source, which is something that we have not yet been asked to do. Additionally, there are multiple inductors in the circuit, so we're going to have to pay attention to that as well. We're still going to approach the problem in the exact same way, though. We're going to analyze the circuit at t is equal to 0 minus, analyze the circuit at t is equal to 0 plus, analyze the circuit at t is equal to infinity, determine the time constant, and then plug things into our generic expression. The fact that this circuit has multiple inductors, though, means that we're going to potentially have some awkward behavior that we have to pay attention to. And what I mean by that is at DC steady state, we will have two short circuits in parallel and no means by which to determine how much current will flow through one as opposed to the other. That being said, our ultimate goal in this problem is not to know how an individual inductor current is behaving. It's to figure out what the voltage drop over the 5 amp current source, how it's behaving. So I would argue that in a problem like this, our first step should be to determine if we can make any simplifications to the circuit that would make our analysis easier. So with that in mind, how are those two inductors electrically connected? Are they in parallel, are they in series, or is it neither?
They're in parallel.
They're in parallel. So that means that I can combine them into a single equivalent inductance. Who can tell me what that value would be?
4.
So because they are inductors in parallel, they add
3 over
like
4.
resistors in parallel.
3
That
over
means
4.
we're going to have 1 times 3 over 1 plus 3, which is 3 over 4, or 0.75 henries, right?
Yeah, I got mixed up.
No problem. And pretty soon we're going to learn a thing to where you no longer have to remember any of that, but we're not quite there yet. So let's redraw this circuit at t is equal to 0 minus, where we're treating our inductors as a single component, having an equivalent inductance of 0.75 henries. Let's see, we're going to have, let me zoom in here a second. All right, so let's see, this is a 4 ohm resistor. This is a 4 ohm resistor. This is a 6 ohm resistor, 12 ohm resistor, this is a 5 amp source. Trying to find this voltage VCS at 0 minus. So the first question I want to ask you guys is our switch open or closed at T is equal to 0 minus?
Open.
Open, all right. So I can leave the top of the circuit as is because I have an open circuit there. The next question that I need to ask you guys is where should I draw my equivalent inductance, which in this case is just going to look like a short circuit. Now, let me draw something here. All right, so the inductance is for sure going to be placed between that node that I've outlined in orange or red and this node that I've outlined in purple. Other than that, it really doesn't particularly matter how we express it. As long as it's connected between those two nodes, we're good to go. And we know that it needs to be connected between those two nodes because those are the two nodes that are shared by the individual inductors, right? So I often get students asking questions of, well, should I put it here, or should I put it here, or should I put it like this? And the answer to all three of those questions is sure, they're all equally valid. So which way would you guys prefer? A vertical line, a horizontal line, or a diagonal line?
I do mine vertically.
So I heard a horizontal and a vertical, so diagonal is just right out from you guys. I think I heard a horizontal first, so let's do that one. And I can erase my node things now since I no longer really need them. All right, so this horizontal line right here represents the short circuit that is our inductor at DC steady state. So we are definitely going to have to know our inductor current at T is equal to 0 minus, because without that, we don't know how the circuit is going to behave at T is equal to 0 plus. So my question to you guys is then, how can we determine either the voltage drop over the current source at T is equal to 0 minus, or that inductor current at T is equal to 0 minus?
We can do nodal and have the reference node be that large node on the bottom, and then find the voltage where those two 4 ohm resistors and that 5 the current source are at.
Okay, so you are suggesting that we do nodal analysis.
Mhm.
I put my reference node here at the bottom, and I try to find this voltage.
Yeah, you just find the voltage right there.
Okay. So that will definitely allow me to calculate that voltage VCS. So that seems reasonable. So I'm going to label this as VCS as a nodal voltage, just because it is representing exactly the voltage drop over that current source. One other thing to consider here to simply potentially eliminate. No, actually, we don't even need to do that for our nodal analysis. All right, so our nodal analysis is really only going to be applying Kirchhoff's current law at the node that the nodal voltage VCS is at. So my current flowing through the 4 ohm resistor is going to be VCS minus 10 volts over 4 ohms. Then I have minus 5 amps because the 5 amp current is entering. And then I have VCS minus my reference node of 0 divided by 4 ohms is equal to 0. And so I can solve this guy and find that VCS at 0 minus is going to be all right, so let's see. I'm going to have minus 10 over 4 minus 5 plus x over 4 is equal to 0.
I get 15 volts.
Okay, I'm just waiting for my calculator to, yep, there we go. 15 volts. All right, so that's what I got, that's what you guys got, so it seems to be a reasonable piece of information. So I'm just gonna put a little box around it. So how could we go about solving for the current IL at 0 minus?
Wouldn't it just be the voltage across the 4 ohm resistor? The voltage drop across that? It's divided by 4 ohms.
So which of the 4 ohm, excuse me, or which of the 4 ohm
I'm sorry,
are you talking about?
the one to the right.
Okay. So what you are suggesting is that the current IL at 0 minus is also this current that I've drawn in, I guess, brown.
Yeah, because the 6 ohm and the 12 ohm are just shorts, so you don't have to
Exactly
look at
right.
those.
Yeah, so the 6 ohm resistor and the 12 ohm resistor are shorted out because they form an equivalent 18 ohm resistance that is in parallel with a short circuit. So we know that any current that flows through this 4 ohm resistor won't split. All of it will flow through that short. So that's perfectly reasonable. So from that, we can say that IL at 0 minus is 5 amps divided by 4 ohms is 1. My pen thingy will work. 1.25. Oh my goodness. Work, dummy. 1.25 amperes. Does anybody have any issues with that analysis? All right, nobody's speaking up, so I feel that we can move forward. All right, so at t is equal to 0 plus, we are going to have a similar looking circuit. Circuit there. Now that our switch is closed, I'm going to have a short there at the top. I'm replacing my inductor or equivalent inductance with a current source. So let's see, 4 ohm, 5 amp plus VCS at 0 plus, 6 ohm, 12 ohm, 1.25 amperes. All right, so we know for sure that IL at 0 plus is 1.25 amps because the current cannot have changed abruptly. How are we going to go about solving for the voltage drop over the current source?
Wouldn't all of those? Oh, never mind. I forgot it doesn't change.
So this looks at a minimum reasonably complicated. So I would suggest that since we are determining a voltage, we may want to use nodal analysis because that will give us a voltage directly. So I'm going to choose my bottom node as my reference node again, just because it's convenient. So I have this node, which is VCS. And I'm going to identify, like I'm going to label my nodes a little bit better this time just because this node's going to be a big one. And we're going to have to pay attention. To what's going on when we do our nodal analysis. So the one in blue is our reference. All right. So the one in pink, we know that that nodal voltage with respect to ground is 10 volts because there's a voltage source there. So that one's easy. We're trying to figure out what the nodal voltage at our orange node is, which I've labeled VCS because it's the voltage drop over the current source. Let's go ahead and just call this guy simply VB for simplicity's sake. That is an unknown voltage. And then down at the very bottom, in blue, we have that large reference node, which we say has a potential of 0. So we're going to have to do KCL at node BCS and KCL at node B. So at our current source, we are going to have VCS minus 10 volts over 4 ohms, just like we had before, minus 5 amps. We're going to have VCS minus VB divided by 4 ohms. We are going to have, so this is all one equation, it's just a little larger. VCS minus VB over 6 ohms. And finally, VCS over 12 ohms is equal to 0. So to be clear, there's 1, 2, 3, 4, 5 different currents leaving node VCS, and I have taken account all 5 of them. Anybody see any errors or issues with my first Kirchhoff's current law equation?
No, sir. That's what I got.
Alrighty. Then we'll do KCL at node B. And so we'll have VB minus VCS divided by 4 ohms plus VB minus VCS divided by 6 ohms plus 1.25 amps is equal to 0. And we're going to need to solve these guys simultaneously. Take a moment. We have a system that is 2 equations, 2 unknowns. So let's see. DCS is going to be my first variable, so I have 1/4 plus 1/4 plus 1/6 plus 1/12. For VB, my coefficients are minus 1/4 plus minus 1/6. For my constant term, I'm going to have 10/4 plus 5. I think that's it. All right, for my second equation, my coefficients for VCS are negative 1/4 plus negative 1/6. My coefficient for VB is 1/4 plus 1/6. And finally, my constant term, when I move it to the right-hand side of the equal sign, is going to be negative 1.25. So I get 75/4 and 63/4. Both of these are voltages. And for those of you like me that prefer to work in decibels, 18.75 volts and 15.75 volts. Those are the answers that I got. Anybody get anything similar?
Yes, sir, I did.
All righty. So the analysis there kind of stepped up a little bit. So now we're ready to analyze the circuit at t is equal to 0 minus, I believe. Or excuse me, no, t is equal to infinity. Pardon me. At t is equal to infinity, and since we weren't asked specifically to calculate the inductor current, I'm not going to bother calculating the inductor current here at infinity. We could do it using mesh or whatever analysis method we feel like, but it's not really relevant anymore. We had to do it at t is equal to 0 minus to figure out how the circuit was behaving at t is equal to 0 plus, and after that point, we are kind of finished with it. All right, so first question, have I redrawn the circuit correctly for t is equal to infinity? So at t is equal to infinity, that's a long time after the switch has closed, so it should still be a short circuit. And we are also at DC steady state, which means we've replaced our equivalent inductance with its DC equivalent, which is a short circuit. So I feel pretty strongly that I've done this correctly. So how might I go about solving for that unknown voltage VCS at infinity that I'm looking for? Yes.
Use nodal analysis. Sorry, that was family in the background.
Oh, no problem. Nodal analysis. Okay, we've been doing nodal and we'll continue to do nodal. Seems reasonable. I'm going to identify my nodes again just to be safe here because things are kind of big and awkward. And so it looks like the only unknown voltage I have is at my orange node, because the pink node is 10 volts with respect to ground. The bottom node is 0 volts with respect to ground. So the only thing that we're really missing here is the voltage at the orange node. So if I write my KCL equation, I'm going to have VCS minus 10 volts over 4 ohms minus 5 amps plus VCS over 4 plus VCS over 6 plus VCS over 12 ohms, and ohms. And all of those are equal to 0. So I can solve. X over 4 plus X over 6 plus X over 12. And I get 10 volts.
Yeah, that's what I got.
Alrighty, so we now know how the circuit's behaving at t is equal to 0 minus, t is equal to 0 plus, and t is equal to infinity. So we need to look, step 4 is determining our time constant, right? We've already determined that LEQ was 3 henries times 1 henry over 3 henry plus 1 henry, because our inductances were in parallel. That gave us 0.75 henry. To look at our equivalent resistance, we're going to need to take our equivalent inductance out of the circuit and then look at a dead network. So that means that my 10 volt source is going to be off. So that's why I replaced it with a short circuit. Here is my 4 ohm resistor. Because we're looking at it during the transient condition, that means that we're looking at it while the switch is closed. So there's my closed switch. Here is my 6 ohm resistor. Here is my 12 ohm resistor. Here are the terminals where we've been connecting our equivalent inductance. So those are the terminals that we're going to be looking in through. Here's my 4 ohm resistor. I have an open circuit where my current source was. So if I'm not mistaken, this is the circuit that I am looking at. So this is my dead network because my voltage source is off, replaced with a short circuit. Current source is off, replaced with an open circuit. During my transient condition, so my switch is closed, and I've taken my inductor out, and so I'm looking in through the inductor terminals. So I think for this guy, I don't know, maybe you guys are smarter than me, but I can't really see right off the bat how the equivalent resistance this guy is going to play out. So I'm going to identify my nodes because I find that that helps me. So that's all one node.
The 4 and the 6 are shorts. Right.
I disagree. at least my cursory examination, and by my cursory examination, I disagree, but I may change my mind momentarily. So there are three nodes. We have a node A, we have a node B, and let's call this orange guy C. So I can see here's A, here's B. There's nothing directly connecting A and B, right? But from A to C, I have a 6 ohm resistor and a 4 ohm resistor in parallel. And from C to B, I have a 12 ohm resistor and a 4 ohm resistor in parallel. So my question to you guys is, has what I've drawn, does that make any sense?
Yes, sir.
All right, because again, it was not, to me, looking at the original circuit, I could not simply intuit how things behaved. So that's why I went to plan B, which is to redraw it in a less awkward form, where that's node C there in the middle. So I can easily see that this 4 ohm resistor and this 6 ohm resistor are shared between nodes A and C, which is why I placed them in parallel between A and C. And similarly, I could see that this 12 and this 4 are between nodes C and B, so they are also in parallel. So let's see, that means that REQ is 6 times 4 is 24 over 10, plus 12 times 4 is 48 over 16. So that's 2.4 plus 3 is equal to 5.4 ohms. If my math is correct, which I believe it to be.
It is. I got the same thing.
Yeah,
All right.
I was about to say it's correct.
All right, so from this, tau, which is going to be LEQ over REQ, is 0.75 henries divided by 5.4 ohms, which I feel strongly is not going to be a nice and even number. .138 repeating seconds. We take the inverse of that. Is 36 over 5. So that's a little nicer. 36 over 5, that would be 7.2, I think. Yeah. Units of per second. Alrighty, so putting all of this together, our current source voltage as a function of time will be, what was the current source voltage at t is equal to 0 minus? Anybody have that written down somewheres?
15 volts.
15 volts, thank you. What was the current source voltage at t is equal to 0 plus?
1.25.
I think that was the current. What's the voltage at t is equal to 0 plus?
18.75 volts.
18.75. What was the voltage at t is equal to infinity? Wasn't that 10 volts?
Yeah, 10 volts.
All right, so that means our voltage at 0 plus minus our voltage at infinity looks like 8.75. There we go. E to the minus 7.2 or 36 over 5t plus V at infinity, which was 10 volts for t greater than or equal to 0 plus. So let me check my answer. I got, at least on my answer sheet or whatever, I got a vastly different answer for this guy right here. So everything else is correct. So that means that my analysis on either when I did it initially or right now about what's happening at either t is equal, what's happening at t is equal to 0 plus must be incorrect. I say that because I know that this guy is correct. I know that this guy is correct. I know that all of that's correct. So the only thing that could potentially be wrong here is what's happening at t is equal to 0 plus. Or, and it's looking very likely, I made a boneheaded mistake and put the current instead of the voltage value in. So let's just double check things just to make sure everything is on the up and up here. This is in-class assignment 15.
Can you go back up to the T at 0 minus? Because I had a question about that current that you found. So you put down 1.25 for that current, where you're saying that the that 6 and 12 are shorted, so you have a current division going on between two parallel.
Okay.
And so
No, I know exactly what you mean. Yeah, so it should, I did 5 over 4, but it should be 15 over 4.
yeah, that's because I was like, what's he doing? I'll just let him go.
Yeah, no, yeah, you should have interrupted me. I was absolutely wrong there. Thank you. That has got to be what's messing everything up there. Okay, so 15 over 4 is going to be 3.75 amps.
Yeah, that would change the equation up for
And then that
T
changes
equals.
this guy
Yeah,
right
1.25.
here to be 3.75 amps. And that's going to change these guys. All right, so I have 1/4 plus 1/4 plus 1/6 plus 1/12. I have negative 1/4 plus negative 1/6. I have 5 plus 10 over 4. All right, and then here I have minus 1/4, minus 1/6, 1/4 plus 1/6, and then negative 3.75. There we go. $11.25 volts goes here. 2.25 volts goes here, which means I should have 11.25 here, which means that this guy should be 1.25. So whoever caught that mistake so early on in the problem, thank you very much for that, because we wouldn't have found an error in setting up the equations or anything because they were done right. So it was a problem prior to that. So thank you very much. You probably just saved us 25 minutes of me going, what the hell did I do? Yeah. And if you see me make a boneheaded mistake like that in the future, by all means, interrupt me and tell me, hey, buddy, you're doing it wrong. That's perfectly okay.
Well, I didn't say anything
Constantly.
because you asked everyone else if you were right and no one said anything. So I thought maybe I was doing something wrong. So that's why I didn't say anything.
Yeah, you know, it is what it is. Like one thing, and it's harder to do, I guess, in these online classes. Actually, it might be easier to do in these online classes. But one thing that I've noticed in my few years of teaching experience that I have, and particularly with engineering students, is that a lot of you guys seem to be afraid to make a mistake. And you shouldn't be, because that's how everybody learns. I mean, I'm a jackass with a PhD in this stuff, and apparently I make dumb mistakes all the time. So it shouldn't be um, beyond reason that, you know, you guys will make a mistake and it'll be okay. So yeah, that all being said, absolutely, if you feel that you're right and I'm wrong, let me know and we'll go through it. I got no problem being incorrect. I would rather teach you the right way than be stubborn. So. All right, so I think we have worked our way through this problem with a reasonably small number of errors, not zero, obviously, but not too many. Any other questions on this steady state sinusoidal analysis that we've been doing for these, or excuse me, not steady state sinusoidal analysis, transient analysis problems that we've been dealing with for the last 3 lectures? Everybody?
I'm good. I mean, you're getting across very well. So thank you.
Sure. Mr. Mogadishu or something like that. Were you going to say something? I feel like I just butchered your last name.
It's actually Moscow, like the city of Russia.
Absolutely butchered it. Mr. Moscow, I apologize. What were you trying to say?
No problem. No problem. I was going to ask, why did you treat the inductors as a short? I didn't catch that immediately.
Okay, so inductors are treated as a short circuit. Do I have room here to do it? Sure. Okay. So
I never got that.
yeah, no problem whatsoever. So the voltage drop over an inductor is equal to the inductance value times the derivative of the current with respect to time, right?
Mm-hmm.
So in a DC circuit, is the current through the inductor changing?
No, right?
Right. For a DC circuit, by definition, nothing is changing. It's direct current, so it's a constant value. So in a DC circuit, this derivative goes to 0, which means the voltage drop over any inductor in a DC circuit must be 0. And because
okay.
the amount of voltage of 0 volts, we're treating it as a short circuit, because a short circuit, by definition, has a 0 volt drop over it while allowing any current that needs to flow through it to flow through it.
Okay.
Yeah,
all
and
right. Thank you.
That same line of reasoning is why we treat capacitors like open circuits. We know that no current should flow through them, and so we replace it with an open circuit in the instance of DC steady state. All right, any other questions?
I'm good, so appreciate it. Thank you.
No problem. All right, well, this took a little bit longer than I had anticipated it would when I talked about it yesterday, but that's all good. We had some very good questions that were asked. Hopefully that clarified some things, and you guys saw how easy it is to make a dumb mistake and how it will wreck your entire thing. So be more careful than I am, apparently, is another thing to pay attention to. All right, so on Thursday, we are going to introduce the topic of the operational amplifier. And then on the following Monday, we will do a little bit more advanced op-amp circuits. Operational amplifiers are not on exam 2. They will be on exam 3. So this is actually the last bit of lecture material that you should expect to see on your second exam. So exam 2 ranges from Thevenin and Norton equivalent circuits all the way through this transient analysis stuff. So it's really not a whole heck of a lot of topics, right? It was Thevenin and Norton, that was lecture 9. Thevenin and Norton with dependent forces was lecture 10. Inductor and capacitor relationships were lectures 11 and 12 respectively, and then we had 3 lectures on transient analysis. So not a whole heck of a lot of widespread material that's going to show up on your test. So I would expect somewhere around 5 to 6 problems, total problems involving Thevenin and Norton equivalent circuits. And I would expect probably a total of 10 problems on your exam to be on transient analysis. And so what I mean by that is it will be 2 circuits, one containing an inductor or one RL circuit and one RC circuit. And then I'll ask you to determine something at t is equal to 0 minus, then something at t is equal to 0 plus, then something at t is equal to infinity, then the time constant, and then give me the final answer. So on the exam, you will be walked through these types of problems step by step in the exact same way that we've solved them in class. So don't do anything crazy squirrely and try to solve them out of order, because that's just going to mess everything up. So anyway, I'm just trying to let you know that the material that we've covered here is roughly 1/3 of your exam. It's actually 40% of the analysis style problems of your exam. So if you're not comfortable with it, practice and let me know, and we can try to schedule some time to review things and stuff like that. Alrighty, I think that's enough yammering out of me. So you guys have a great rest of your week or whatever, and I'll see you on Thursday.
All right, see ya. Thank you, Dr. Hartman.